Equilibrium video 2 is on potential energy diagrams. So we're going to look at potential energy diagrams. And so another term we need to know is the activated complex. That is the unstable intermediate between the reactants and the products. You need at this point to pause the video so that you can draw this diagram and label all the parts. And then when you're done, you can hit play again, and then I'm going to explain to you what all the parts mean. Alright, so our x-axis is the reaction progress, and our reaction goes from reactants to products. We can also read this in the other direction. So reactants to products is called our forward direction. It's known as our forward reaction. Products to reactants is known as our reverse reaction. Okay? So you can read these diagrams in both directions. Most often, if it's not specified what direction, we're talking about the forward direction. Alright, so we start off with our potential energy of our reactants. So our reactants have a certain amount of energy to begin with, and that's what is represented here. So potential energy of our reactants in this diagram would be 120 kilojoules. Over here we have our products, and this line here represents the potential energy of our products, which in this case is 220 kilojoules. And then at the top of our hill here we have our activated complex. That's that unstable intermediate. And it has a potential energy as well. And in this case it is 280 kilojoules. And then we have the activation energy for the forward direction, meaning from the reactants to the top of the hill. That's the activation energy for the forward, reactants to the top of the hill. And that is the difference between the potential energy of our reactants and the potential energy of our activated complex. So that is represented by this interval here, A. So if we had to calculate that, it would be 280 minus 120. And so our energy of activation would be, again, 280 minus 120, which would be 160. Right? And then we have another piece here called the heat of the reaction, or energy of the reaction, also known as enthalpy, which is represented by delta H. Right? And that is this interval B right here. And that's the difference in potential energy of the reactants and the products. And that delta H is always calculated by doing products energy minus the reactants energy. So if the product's potential energy is 220 and the reactant's potential energy is 120, then the delta H is 100 kilojoules. The other thing we can tell from this diagram is whether or not it's endothermic or exothermic. If your delta H comes out to be positive, just like in our thermo unit, that means it is endothermic. If it is negative, then it is exothermic. So as long as you're excuse me, as long as energy increases from reactants to products, that's endothermic. If the energy decreases from reactants to product, meaning your reactants have higher energy than your products, which would be way down here, then that would be exothermic. Energy will be released. Alright, so to sum up the different letters on the potential energy diagram, you'll want to write these down. Interval A, again, was the activation energy, the forward direction, reactants to products. Interval B was their enthalpy or heat of reaction, and that is products minus reactants. Interval C was the potential energy of the products. Interval D was the potential energy of the reactants. And interval E was the potential energy of the activated complex. Again, you're going to make sure you have those written down, because you will be asked to diagram, to label a diagram and also answer questions about a diagram. Just like the one you saw a minute ago. So you might want to pause so you can write all those down, because I'm going to continue on. So if we're going to look at diagram 1 in your notes, you will see I did not draw diagram 1 because diagram 1 I drew here was this diagram we just had a moment ago. And so number 1 says which letter is the energy of activation for the forward direction? Again, that's interval A. Question 2 says what's the energy of activation in kilojoules? So how much energy does the interval A represent? So again, that's the difference from 280 to 120, and that's 160 kilojoules. Number 3 wants to know what is the delta H. Delta H is the difference between the energy of the reactants and the products. Always products energy minus reactant energy. And so that's going to be 220 minus 120. Oh, actually in your diagram it's 260. My fault. So it should have been up here. Sorry, your diagram is different. I apologize. So 260 for your diagram. So the difference would be from 260 to 120, and that would be 140 kilojoules. And question 4 wants to know if it's endothermic or exothermic, and since our product energy is higher than our reactant energy, that is endothermic. Alright? So again, to sum up those answers here. Oh, sorry, and then question 5 says what would a catalyst do? Question 5 wants to know what a catalyst would do to your diagram. A catalyst lowers the activation energy, so basically it lowers the hill that is required to get over to the products. Alright, so basically it just lowers this activation energy. Okay? So that you can get to the products more easily with less energy. So again, these are the answers. 1 was A, 2 was 160, 3 was B and 140 kilojoules. 4 endothermic, because the products have greater energy than the reactants. And 5, it lowers the activation energy, and on your graph you can see that because it would lower the hill. Alright, so I want you to stop in a video, and I want you to do diagram number 2. Once you're done, you can hit start or play again, and then you can check your answers. These are the answers for diagram 2. Please make note of whatever questions you have and be ready to ask them to me tomorrow when you get to class.